Have you ever stopped to think about what actually keeps our crazy, hyper-connected world running so smoothly? Well, I can tell you it's definitely not magic. Behind every single video stream, every click, every bit of data, there's a network that was built on incredibly careful planning. And today, we're going to pull back the curtain on one of the most vital parts of that planning, the fiber optic loss budget. It's the secret sauce, really, that decides if a network is going to be a champion or a total failure. So it all starts with a simple fact. Fiber optic cables move our data around as tiny pulses of light. We're talking about these impossibly thin strands of glass, some no thicker than a human hair, that make up the backbone of all modern communication. They carry our information at something like 70% of the speed of light. It's just amazing. But of course, there's always a catch, right? As those little light pulses race through the fiber, their signal strength naturally gets weaker and weaker. This effect is called attenuation, and it's the #1 challenge we have to solve. Because if that light signal gets too dim, well, the data it's carrying is just gone. Poof. And that brings us to this really delicate balancing act. See, the goal is to make absolutely sure the optical signal gets to where it's going with just the right amount of power. Not too weak, but also not too strong. Okay, so let's really get into this puzzle. If the signal shows up and it's too weak, the receiver on the other end literally can't see it. That leads to errors in the data, or worse, the whole link just fails. But on the flip side, if the signal comes in way too strong, it can actually overload the receiver and distort the signal. It's kind of like someone shouting directly into your ear. You know they're talking, but the message just turns into garbled noise. And this is more critical now than it has ever been. As our network speeds just skyrocket, we're talking 400 gigabits per second, even faster, that perfect window for signal power gets incredibly tiny. The margin for error basically vanishes, which makes this whole balancing act absolutely essential for getting high performance. So you might be wondering, how do network designers actually solve this puzzle? Well, they use this fundamental tool called an optical power budget, or sometimes a link budget. And you should think of it just like a financial budget. You've got a certain amount of power to spend to get your signal from the transmitter all the way to the receiver. To put it simply, the link budget is your total allowance for loss. It's the absolute maximum amount of signal power, which we measure in decibels, or dB, that can disappear along the way before that link just stops working correctly. So our budget calculation starts right here, with the transmitter's launch power. This is the initial strength of the light signal as it blasts off from the starting line. In our example here, the transmitter is putting out -8 dBm of power. And the finish line, that's defined by the receiver's sensitivity. This is the absolute bare minimum power level that the receiver needs to have in order to correctly pick up and understand the signal that's coming in. For this one, it needs at least -34 dBm to do its job. And now for some really simple math. You just take the transmitter's power and subtract the receiver's sensitivity, and that gives us our total budget. So in this case, we have 26 decibels of power that we can afford to lose along the journey. That is our total spending limit. Okay, so we have our budget. Now it's time to look at the expense report. Where exactly does all that precious power get spent as it travels down the fiber path? It really comes down to 3 main culprits. First, the cable itself, that causes attenuation. The longer the cable, the more light you're going to lose. Second, every single connector pair where you join 2 cables together, that introduces a little bit of loss. And third, splices, which are these permanent fusions of 2 fibers. They also take a small toll on your signal. Now, this is where it gets really useful. Industry standards like the TIA 568, they basically give us a price list for all these different losses. These are the maximum kind of worst-case values that we should plan for. A connector pair could cost you up to 0.75 dB, a splice up to 0.3 dB, and the cable itself, well, that is a cost for every kilometer. These numbers are the fundamental building blocks for our entire calculation. All right, so we've got our budget and we've got our price list. Let's put it all together and actually run the numbers on a real-world scenario. The calculation itself is actually pretty simple. You just add up all the potential losses. So we'll add up the loss from the fiber's length, the loss from every connector, and the loss from every splice. And this part is so important, we add in a safety margin. This is to account for real-world stuff, like components getting older, future repairs, or even just tiny bends in the cable. Okay, let's walk through this example. Imagine we have a 40-kilometer link, and it's got 2 connector pairs and 5 splices. First up, the fiber loss. That's 40 kilometers times a pretty typical loss of 0.4 dB per kilometer, giving us 16 dB. Next, the 2 connector pairs. At that worst-case value of 0.75 dB each, that adds another 1.5 dB.
Then our 5 splices. At 0.1 dB each, tack on another half a decibel. And finally, we add a nice, healthy 3 dB for a safety margin. So our total estimated loss comes out to 21.0 dB.
And now, the moment of truth. Our available link budget, if you remember, was 26 dB. Our calculated total loss is 21 dB. And since our spending is well below our budget, this link gets a big green pass. This means, at least on paper, this network design is totally viable and should work just fine. But hey, the calculation is really just the beginning. A truly successful network isn't just built on spreadsheets, right? It's built out there in the real world. So let's talk about what it means to design for reality. Now, this right here is a fantastic piece of industry wisdom. You don't just want to be under budget. The best practice is to aim to use only about 70% of it. This super conservative approach gives you a massive buffer. It helps make sure the equipment works perfectly on day one, and it really future-proofs the system against things getting older or maybe future changes. And you've got to remember, the real world is messy. A loss budget is a great estimate, but it's not a guarantee. That's why using high-quality components really matters. It's why meticulously cleaning every single connector is completely non-negotiable. I mean, a single speck of dust can be a total disaster. And it's why proper installation, like never bending a cable too tightly, is just as critical as all the math we just did. So I'll just leave you with this thought. The difference between a network that is robust and reliable and one that's constantly on the verge of failing, it often comes down to this kind of meticulous planning. A proper loss budget isn't just about getting a signal from point A to point B. It's about building a solid foundation of reliability for our entire digital world. So is your network ready for the future? Or is it maybe one dirty connector away from going dark?